Hello there, viewer. My name is Mystery Man, and right behind me I have a serialized binary multiplier. And this one in general for our little example is a 4-bit multiplier and can have a max output of 8 bits. And I'm going to demonstrate for why serial multipliers are actually very powerful, and rather the serial adder I made. If you have not seen my serial adder, I highly recommend you to check out the video in the description, and it'll teach you how to build it. Because you're going to need to know how to make this, because I'm not doing a tutorial on the multiplier. Okay, so for some test inputs, I'm going to do something. I'm going to do 5 times 3 as our first test. And all I have to do is clock it. And our output will come out of the register in a few ticks. Okay, and there's our result. It's 1. So as you can see, we have 8 plus 4 plus 2 plus 1. If you add all those together, you get 15. And we have 15 in that register, so that's good. And the cool thing is if you want to actually extract this data, you could just turn this lever on and have the data flow out. Okay, so now that we've done that number, let's go and do another one. I'll do 5 times 5 this time, so that we get 25. Okay, carry it, redstone dust flashes, all that fancy stuff, and there we have it. So we have 1 plus 8 to get 9, and then if you add 16 to 9, you get 25, and that's correct, because 5 times 5 is 25. Alright. Now I'm going to go ahead and do another number. Let's do 6 times 7. That one's a good one. So I'll put 6 in the B. So 4 and 2. And then we're going to do 7 in the A. It doesn't matter. These are interchangeable. And then this just goes in, goes through, and there's our result. So we should get 42. So we have 32 plus 8, which is 40, plus 2, that is 42. And the answer is correct. Let's go ahead and reset. And then we'll do one more calculation before I go into depth on how this thing actually works, because it's actually pretty quick for a 4-bit multiplier. And it's not parallel at all, it's serial. So let's go ahead and do a 15 times 15, the full amount we can actually do. And then, yeah, and then I think that'd be good enough. So calculates the answer, and there we go. So we got 128 plus 64, which will become, let's see, that is 192. And then if we add this to 192, we get 224. And then add 1 to 224, we get 225, which is correct. So yeah, 15 squared is 225. And now, that is that. So I've basically shown you that, yeah, we can multiply two 4-bit numbers. But how does it work? I think the first thing I can demonstrate is actually how multiplication works in binary. So I'll do that right over here. And then I'll go into depth on how my serial adders can be chained up this way. So let's go ahead and do this. So let's say we wanted to multiply two numbers. I'm going to multiply 5 times 3. Why not? It's a really good and easy example. So here's what a basic multiplication in binary looks like. We'll need our output here. Essentially, we start at the 1 bit here, and we do, what's 1 times 1? Well, 1 times 1 is 1. And then we check what is 1 times 0. Well, 1 times 0 is 0. And then we check what is 1 times 1, and we get 1. So 1 times 5 in this case is just 5. And now we go to the next position, just like normal multiplication that we always do. So now we check, okay, how many times does 1 go into 1? It goes in 1 time, although now it's shifted over, right? So keep that in mind. And now we have 1 times 0, which is 0, and then 1 times 1, which is 1. And now all you have to do is add the partial products, which are these partial parts we've just found. So it is as quite simple as adding 1 plus 0, which is 1, 1 plus 0, which is 1, 1 plus 0, which is 1, 1 plus 0, which is 1. There's our answer. So 5 times 3 is 15. And that's how you do binary multiplication, like a very rough breakdown of how it works. So yeah, how does this serial adder actually do this? Well, the first thing I had to figure out is how to actually calculate the amount of times I needed to shift. So here's what I did. So for the ones place, I don't shift at all. I use a repeater. For the twos place, I add a 3-tick repeater. And this, in serial in Minecraft, is equal to a shift to the left for this guy. It's basically a delay is a shift to the left, and a value that's earlier than this is a shift to the right. So you already have basic shift operations. And basically I just add 2 repeaters for 4 and then 3 repeaters for 8. Because this is the same as saying 2 to the power 3, 2 to the power 2, 2 to the power of 1, and then 2 to the power 0, which is nothing. It's just 1. And now you understand why I have repeaters there. And believe it or not, all you have to do is just take the serialized input and OR them with all of these shifts. Now, the B register here is responsible for allowing certain numbers to go through certain shifts. And this represents the 1 times 1 scenario. If 1 times 1 is equal to 1, then we need to use an AND gate for this. So this is an AND gate because it only works if this lever's on and if this signal's on. You can't have it one or the other. So that mimics the actual multiplication. And then these 3 serial adders are the things that sum up the partial products. So essentially you can just have your A's go in here, and your A's will sum up to that partial product. So if you watch my serial adder video, you'll notice that the adders pretty much synchronized. So you can have these adders next to each other, and then you can have the outputs go into another adder, and then that is the final partial product sum, and it goes out here. So that's essentially all there is to multiplication. It's literally just using AND gates to select which shifts you want to allow through, and then you sum up those partial products. So now let's go ahead and do another calculation, like 7 times 7, which is going to be like this. Unfortunately, my register is wired weird, but believe me, that's 7, and that's going to be 7. So you'll notice that some of the outputs here are obviously going to be delayed as we allow it to go through. So just watch those repeaters. You can see they're delayed, and they just ripple right through, and you get your output really quickly. Like, I know that's 49 because it's 48 plus 1. So as you can see, this 4-bit binary multiplier is actually comparable to most multipliers you would see with parallel adders. And the reason why it's that good is because while we're calculating 1 bit per thing, it's also sending it to the next thing to be calculated. So it's instantaneous. It's not instantaneous, but it's like it's got this data flow that's constant and consistent, and it just works out. So I hope that gives you some ideas to what you need to do. So yeah, remember, just go ahead and add this to your inputs just like so with the adders. Just make sure the adders are spaced out like that. and then get the outputs to hook into the last adder, and then that into your output. Okay, so essentially, yeah, we need this line right here to do something for us. So what I have is this wire that goes down here, and it's set on a specific delay that allows the repeater locks to lock the answer. So this has to be 1 bit ahead of this adder, so yeah. That takes care of that. Now if you want an 8-bit multiplier, it's really simple. Just copy this section. You have to make these AND gate sections bigger though, but you can basically just keep tiling it in the same fashion and they'll all converge to this one adder at the end. So I hope that demonstration was fun. Go ahead and hit the like button if you thought this was interesting, and I'm going to be making a serial-based divider very soon, which should be very cool because it's only going to use one serial adder on subtraction mode. So yeah, it's not going to be as big as the multiplier, but it does mean it will be slower. So anyways, I hope you'll enjoy. See you later.